Hey everybody, welcome to the August webinar session. I'll give a few minutes for people to join here. So while we're doing that, I'll go ahead and introduce myself. So I'm Travis Reynolds. I am going to be the host for today's webinar. I am your Vice President of DSUA. So it's good to be here. I've kind of been in the background for several of them in the past, but Jerry asked me to be up front on this one. So whether that's for the best or not, that's here I am. So as people are coming in, go ahead and walk through a little bit about DSUA. So DSUA is a nonprofit organization. We've been around since 2008. Our primary objectives are to promote the collaboration and innovation of dry scrubbing solutions. That basically includes SDA, CDS, and we've kind of started to make an effort to roll in DSI as part of that in the past 2 years. We also want to develop and provide a venue for OEMs, operators, end users, suppliers to network with one another. So as we've talked about in the past, we did decide to suspend the in-person conference for 2021. We did announce, I believe in the last webinar or a couple webinars, that we were partnering with Enviro Summit for their in-person conference this year. That has now been suspended as well, or postponed until April because of the increase in COVID and just trying to take into consideration personnel safety for that. So that will still be at the Sheraton in Charlotte, North Carolina. There will still be a dedicated breakout session for DSUA, and we are accepting abstracts for that. So if you want to submit an abstract for that, you can go to the Enviro Summit website and you can do that, or you can reach out to Jerry or myself, and we can get that pushed in for you there. So you can find out more about the Enviro Summit at the bottom of the DSUA homepage. There's also a discount code for the Enviro Summit conference for DSUA members, so you can reach out to us and we can give you more information on that. These webinars are recorded, and after they are recorded, we load them up to our YouTube channel. It usually takes a few days because we have to go through and make sure that there's been no glitches and get approval from everybody to load that up. But usually within the first, I'll say 5 days or so, they're usually loaded up to YouTube. So you can go there, you can replay it, watch it, pause it, do whatever you want to do there. So it's a really good way to follow along, and we've had a lot of feedback from people watching and participating in that, saying that they really appreciate that format. At the end of this webinar, or when you choose to leave, if you have to leave early, you should receive a prompt for a survey asking for feedback on this webinar. We're trying to get feedback from all participants going forward to see if we can try to, learn from your experiences, your perception of this, how we can make this better. If there's something we're doing that you like, let us know. If there's something that we're doing that you don't like, let us know. None of this can be possible without our sponsors. And we really appreciate the contributions that the sponsors have made this year to help this happen. It's been a crazy year, and this wouldn't be possible without them. So with that, I'm going to roll through some slides that we have here to just highlight a few of the sponsors that we've got currently. Okay, hopefully this is sharing now. First sponsor we're going to talk about is Reaction Analytics Solutions Corp. They are they specialize in engineering solutions using computational fluid dynamic modeling. The founder, Dr. Guisu Liu, has worked in the industry for over 20 years, and he's prepared over 100 CFD-based engineering designs and optimization projects for utilities, engineering firms, industrial owners, etc. Their experience covers everything from front-end furnace combustion to back-end flue gas treatment systems. Reaction Analytics Solutions also uses their specialized CFD modeling to help end users find cost-saving optimization solutions for sorbent injection rates for acid gas and mercury control. You can check out the May 2021 DSUA webinar on YouTube from Dr. Guisu Liu about how they use CFD modeling to help optimize dry scrubbing solutions. Next is Primex. If you've been around the DSUA for very long, Primex is a name you're very familiar with. They provide comprehensive programs to help SDA, CDS, and DSI users optimize dry scrubber performance. With 20 years of customer success behind them, they bring a unique combination of knowledge, technology, and patience to their customers. I'm going back to Guisu. Stuart Nicholson has been involved in the DSUA for a number of years in various roles and capacities, and we really appreciate his contributions over those years. You can go back to the November 2020 DSUA webinar on YouTube, where they presented a paper on implementing approach temperature control for a CDS at Dry Fork Station, or you can also go to February 2021, where they presented on optimizing SDA performance by detecting slurry atomization operation. IGS, they are an international provider of surface protection and material handling solutions headquartered in Virginia. They have over 30 years of experience helping customers solve metal wastage, ash accumulation, and general liability problems in mission-critical equipment. They are an industry leader in development and application of solutions for corrosion and erosion problems in challenging operating environments. You can go back to the June 2021 webinar where IGS presented on presenting corrosion-related failures in SDAs. GE Power, that's who I work for actually, they offer steam power technology upgrades for fossil and nuclear applications, including boiler generators, steam turbines, AQCS, and digital solutions to help produce power efficiently and provide performance for the life of a power plant. GE has over 30% of the global steam turbine capacity and 50% of steam turbines for nuclear power plants, as well as 30% of the world's boilers. They're able to help customers from best-in-class upgrades and retrofits to core operations and maintenance across more than 90 OEM brands, utilizing their 6,000 field service employees. You can go back and look at the September 2020 DSUA webinar where TVA talked about the NID installation at Gallatin that was supplied by GE. Carton Fujikin, they are ceramic control valve manufacturer that's been in the business for more than 45 years and utilized in this country now for more than 35 years. Their valves are designed for erosive, corrosive material or media services such as lime slurry, recycle slurry, gypsum, and coal-fired power plants. Their ceramic control valves have been utilized in a number of industries, including pulp and paper, chemical and refining, in addition to the power industry, for handling a variety of erosive materials and services. And finally, for this commercial presentation portion, we got Lewast. Lewast North America is a Lewast Group subsidiary. They're a global limestone, lime, hydrated lime, and silicate minerals company. Lewast supplies high-quality calcium-based products, including Sorbical SP and SPS, enhanced hydrated lime sorbents to neutralize acid gas and the flue gas generated by combustion and industrial processes. Lewast sorbents are applied across numerous industries, including fossil, waste to energy, power generation, cement, glass, pulp and paper, chemical manufacturers, etc. Jerry Hunt, our president of DSUA, actually works for Lewast there, and that's a pretty good lead into him. He will be the moderator for today's webinar. So with that, I think everyone here knows Jerry. He's no stranger to this, and Jerry, I'll hand it over to you.
Sounds good. And hopefully you can see the screen here. We pop up at the end. So I'm going to introduce our first speaker. Our first speaker is Dave Luchtenberg of Aep. Those of you who've been around the DSI industry, you guys are familiar with Aep. You're familiar with Dave Luchtenberg and everything that they've been doing with DSI solutions. Dave has his bachelor's in chemical engineering from The Ohio State University, and he's been at AEP for 15 years and an environmental engineering role. And he's currently an engineering principal at AEP, with one of his primary responsibilities and overall just optimizing the performance of their large DSI system fleet. So I'm sure his roles are vast, and this is just one of many, but I'm going to be navigating Dave's slides. Dave's calling in for us. So Dave, I'm going to turn over to you, and let you run with this and give the presentations, and just let me know when you're ready for me to go through the next slide.
All right. Thanks, Jerry. Can you hear me okay?
Yes, sir.
Okay. So just to give a little background, AEP does not allow us to use Zoom. They kind of put that edict down very early on in the pandemic that Zoom was verboten, and it turns out, you know, Zoom is sort of like Kleenex or other ubiquitous products where everyone knows that a video call with a conference call is that's, you do that on Zoom, of course, right? Well, I don't. So anyways, I'm at a bit of a disadvantage. So I'm here to talk about using dry sorbent injection at the SCR inlet and some of the stuff that we've learned as a company with AEP. I'm happy to do that, and go ahead and push it to the next slide.
All right, we're there.
Okay, so DSI, this is sort of a filler slide a bit. It's really a very simple process, right? So the concept is we use a dilute airstream to inject into the duct a measured product of some sort of a dry alkaline powder, which is meant to scrub some sort of acid out of our flue gas. The advantage is that the system is fairly cheap to build, so it's a low capital cost, but then that reagent that we're using, it tends to be, you know, it started off as a somewhat reasonable cost, and you know, as they add more foo-foo stuff into it, it becomes more and more expensive. Jerry can tell you all about that. Sorry, I had to do that.
That's fair.
So we have two different fundamental designs for our DSI systems. We have the ones that were built for SO3 control. So those were built in conjunction with the wet scrubbers that we put on our coal fleet. And those all units were set up in that 2005 to 2012 range. And then as a follow-on to that, we built two additional slightly larger systems that were meant for HCl control, and where they were built in response to the MATS rule that came out back in, I think that was promulgated in 2013. And that's our Northeastern and Rockport plants. And most of the rest of this slide, or this slide deck, is going to be focused on Rockport and some of the stuff we've done there. So I put in a couple slides from the original testing that we did that gave us the confidence to go ahead and, so we're on slide 3 now, that gave AEP the confidence to proceed with using DSI as our, quote unquote, as our FGD. So we needed, I believe I took the units off of the X and Y axis here, but in general, we needed roughly 90% HCl removal to get there. And I imagine if you sit there and count the grids, you can figure out what the Y-axis is. And we were able to get there with milled bicarbonate, and that's what we're using at Rockport now. So if you go to slide 4, I really like this one a lot. I'm not going to take credit for it. Doug Ritzenthaler put it together. His name's on the bottom right corner. What this shows that was part of our decision tree was that, you know, we were worried about maintaining mercury in conjunction with HCl removal. And, you know, the green box at the bottom left is where we had to land for the solution to work. And so in some instances, we had too much mercury, even though we had HCl under control. In other instances, mercury was okay, but HCl was out of bounds. And so what we figured out in the process of this original pilot test was that we had to use brominated activated carbon for mercury control, and that sodium bicarbonate was really the only sorbent that was going to work in this application. I think that yellow wedge represents there was a proposed versus the actual limit, and I believe the 1.2 is the actual number for mercury. So with slide 5, you'll see this was our original system arrangement. You know, there was no SCRs, you know, it was pretty simple setup, shared stack. You know, we burn 87-13 blend, 87% PRB, 13% Eastern bituminous, but it's like the 9-mex grade, so like a 1.2 pounds per million SO2. And that gets us to a blend that lands somewhere in the neighborhood of 0.55 to 0.6 pounds per million SO2 per million. And that's really what DSI for this application only works when you have a pretty low sulfur content. You know, this is each of those units are 1,300 megawatt units, and we're using quite a bit of sodium sorbent to scrub that down to acceptable levels. And so the original setup was to inject in front of the precipitator, and the precipitator would sort of act as our absorber vessel, so to speak, and it just goes straight to the stack after that. So next slide, when you know, AEP, I imagine the utility folks know a fair amount about this, but maybe folks in other industries don't. We've gone through a series of negotiations with EPA to resolve our new source review consent decree that we entered into several years back. And as part of that, Rockport was listed as something that we were going to have to scrub in some fashion, something much stronger than what we were doing for HCl control. So I was given the task of setting up this pilot test to try to determine what can be done to improve the removal performance at the unit. And at this point, we had already had an SCR installed on one of the 2 units. And so we sort of took an all of the above approach. So we looked at putting in Cobra lances upstream of where we inject ammonia at the SCR in Unit 1. We also looked at direct injection onto the delta wings, so sort of in parallel with ammonia injection. And then for we brought in a series of Noltex product, which is the Sortec injectors, which are basically you take each individual nozzle and you add a little mini compressor to it to disperse the product into the duct. And so we had that at our existing air heater outlet injection location. And we looked at, you know, each of the different strategies separately. And we also looked at the combined injection of both to see if that would have been something we would need to do to optimize our system. So we should be on slide 7 now. And this shows a screen cut of, you know, we've got several more of these, but this shows all 3 of them side by side by side. So this shows the 3 different options we were looking at for injection at the SCR. So on the left, what you see is a single injection nozzle centered on each of the 4 delta wings going across the duct. So it might be a little confusing for you, but if you see there's like maybe 4 discs that are sort of embedded in there where all the color starts, those are the delta wings where it was engineered for dispersing ammonia. And so the concept is if it's engineered to disperse one chemical, which admittedly is a vapor, it stands stands up that you would think that it should also be able to disperse a fine powder in a similar fashion. The middle animation shows 8 cobra lances sort of evenly dispersed through the ducts. And the idea here was, the cobra lances have their own sort of built-in dispersion to try and push the product out into the duct. And if we put that upstream of the cobra lances, or I'm sorry, of the delta wings, then maybe the double dispersion would have an enhancement effect. And then the third image on the right shows 2 sorbent lances directly injecting onto the delta wings. Now there was more slides to this, and what was shown was that the 2 lances per delta wing was going to be our best bet. Now, admittedly, that was performed by the folks that provided us with the delta wings. So we decided to take a conservative approach, and we put delta wing injectors on all 3 ducts, but we also put in as many cobras as we could get there in a 6-week period. And so we looked at both separately. Now, if you go to slide 8, this is a duct drawing that shows basically the geometry of why this works. So if you consider the flue gas flow is up in this view, what happens is you push the material onto the delta wing, and there's a sort of a mini cyclone effect where you get sort of a recirculation around that delta wing. And what that does is it disperses the material through the cross section of the duct. And what I've got here on the next slide is a video. And if you want to go ahead and press play on it,
Right. We're playing.
You're looking up. You're looking up right now. You see the scaffold that was set in place to access the injection nozzle above you. So now he's pushing through the nozzle and should be into the flue gas stream. You see the sorbent nozzle above you. It sort of forms. In this view, you can see it's kind of probably too close to the delta wing. That's something we can fix. But it forms like a little volcano right there because of the proximity. But in general, you can see where it's just sort of dusting everything. And as it sort of moves, he's looking at the outside. You can kind of see the rotation of the flow around the delta wing. And I think he'll go to both sides of the delta wing.
Yep. Now we see the other side.
Yeah, so I think we're pretty well in alignment here. I'm sort of playing it on my end here also.
I was going to say, David, I want everyone to know the fact that we're watching this independently. Your narration was spot on with what we were seeing, which is, I'm going to say that's impressive coordination right there.
Pat yourself on the back, Jared. Good job.
I'll take what I can get.
Yeah, every once in a while you'll see sort of a slough of like maybe an accumulation of material, and I think that's just sort of the nature of that volcano that forms. So there is a proximity that you need to get right of the end of the nozzle to the edge of the delta wing. But in general, what I really like about this is that there's no restriction or any sort of impediment to flow of the material coming out of the pipe. All it is an open-ended pipe, and we're using the geometry of that delta wing to cause a mini vortex and spread the material out into the cross section. It's simple and elegant. It really meets what I like to follow in general with any sort of engineering design, which is the KISS concept, which is, keep it simple, stupid.
Well, to add some perspective, having seen duct camera videos when there was just a lance of that design with no delta wing, the difference of what you see in terms of the turbulence and the sorbent plume, like it's a pretty substantial and impressive difference to visually see that with these duct camera videos. So this was a pretty cool one to share. Thanks, Dave.
Absolutely. A video really, I'm a learn by doing type of person. And if I can see something, it helps me quite a bit.
For sure. We do have a question that came in before we move on officially to the next slide. The question was, have you had any experience with any kind of erosion or corrosion when it comes to injecting any sorbents directly in conjunction with the delta wings?
Well, we have had, we've had SCRs installed on our units for 20 years, right? So we have had corrosion issue or erosion issues. You have to remember, these are all high dust environments, so they're also getting sandblasted by fly ash. So we've had erosion issues. I think there's been incidents where one of the delta wings has dropped off its support down a level. But I don't know that it's necessarily been attributed to sorbent injection. I think it's just more, natural wear and tear from getting hit by fly ash.
So do you think that that's a great point. And do you think that there is a shelf life associated with these delta wings that either they need modified or inspected every so often to ensure that the integrity of the distribution that you're intended to get? Is that something you guys kind of have?
Oh yeah, that is part of our PM program. We AEP in general, we are big believers in maintaining our systems to the greatest extent possible. I mean, now on one hand, you can't spell cheap without AEP, all right? And that's been said to me many times in my career. But when there are certain things that can save buku dollars, such as dispersion, it helps to have a bigger system there to maybe sort of carry some of the load on getting that work done. So dispersion for ammonia is a big deal. We don't want ammonia slip. We don't want to waste ammonia. So we do have a program in place to regularly inspect and repair as needed. That's a good question, so thank you.
Yeah, thank you, Dave.
So we're on slide 10. So this is showing the same. This is showing sort of the same view as I had 2 slides ago, except this is a front view. So the ammonia nozzle is shown in the middle, and the red box more or less shows the target area that I was sort of verbally described to me as where you want to stay within for getting good dispersion off your delta wing. Either you have something directly in the center line, or maybe just directly below the ammonia nozzle, maybe 12 inches or so below, or in the same center line as the ammonia nozzle on either side. So if you can sort of stay within, and each duct is a little different, each delta wing is a little different. It sort of depends on, I'm not going to give hard and fast rules for how far side to side you can go or up and down, because I don't think none of our units all have the same delta wings configuration. So it's slightly different, but in general, you want to stay fairly close. You don't want to go any higher than the existing ammonia nozzle, and you want to stay within a few feet either side.
That's a great point, Dave, in terms of using it in conjunction with the ammonia nozzle. Have you guys had any, was that something you guys figured out from experience, or did someone kind of say, the DSI nozzle should go relative to the ammonia nozzle because of reasons X, Y, and
so
T?
that
How
was,
did you guys figure that out?
that was something when we did the CFD model, that was with Riley Power, and they own the patent on the Delta Wings. And that was when we sort of went back and forth on the different nozzle configurations. This is something that came out of that discussion. All right, so if you go to slide 11, that shows the current equipment arrangement for Rockport. So we now have SCRs installed. We're injecting anhydrous ammonia that gets made down with air, and we're also injecting DSI in parallel with it. So on slide 10, that actually is one of the that's a cutaway from one of the duct drawings for Rockport. So that is our arrangement at Rockport. We have an ammonia nozzle that's on the center line, and then we have two sorbent nozzles on either side. Now, one of the things that we improved on with the new Rockport system is the way we disperse the material. Now, we used to have 3 equipment stack-ups, and one injection stack-up was intended for a specific duct. And what we did was we sort of broke away from that setup, and we made it to where we only have 2 stack-ups required in service at any one time, and they have a complete overlap on the entire unit, such that if you're on slide 10, the injection nozzle on the left would come from one of the stack-ups in service, and the nozzle on the right would come from the other stack-up in service.
Got it.
So while it's not a complete overlap, it's much, much better than what we had before.
Got it.
So if you go to slide 12, this, I actually did not scrub this one, but these curves are a bit out of date, but they're illustrative nonetheless. So what this shows, this is a normalized stoichiometric ratio for, and so what that means is the green line is ideal conditions. So if your injection is on an NSR of 0.5 and you're getting 50% removal of your targeted acid gas, then you're using every last molecule of sorbent that is available. So you're not wasting any material. So the lower your NSR, the better off your performance is. And so when you look at these 2 different curves, so the baseline is what we were getting with air heater outlet injection, and Delta Wings was our clear winner in the pilot test that I had to sort of run on a fire drill type of approach. And reading straight across, if you look at say 60, or really the extreme case would be 70% removal, going from an NSR of 2.1 to an NSR of 1.1 or 1.05 to get 70% removal, that's like you've cut your usage in half, and that's millions of dollars for us. So that was a big win.
Dave, was that based on changing an injection location as well, like moving upstream of the SCR,
yes,
or was that?
Yes.
Okay,
so
those
okay. 2 curves, the 2 curves represent, so the red dotted represents what we were getting with just injecting at the air heater outlet. And then the purple dotted represents what we got with delta wing injection.
Okay, so there's a
So, I mean,
benefit. You got
shifting to the
distribution,
left
temperature.
was a
Gotcha.
huge deal. Yes.
Wow. Makes sense.
So I've got another slide here that sort of shows some of our lessons learned. So I'm not going to take a huge credit for this. I think Chad Donner was probably the person that sort of led the charge on this one. But you really need to dehumidify your injection air, and for calcium products, you really want to stay below that 5% relative humidity. We're using that also with sodium products. That's a good target to hit. It's not terribly onerous from an equipment perspective. You can get there with the fairly modest investment. One thing that we're starting to get away from, we used to vent our stack ups up into the silo roof. The idea was to try to minimize leakage that would happen inside the silo skirt, but it turns out that you really just need better maintenance to minimize leakage. That systems leak plenty when they're vented up to the top of the silo. So we're sort of going down that path of putting in filters on top of our weigh bins to vent into the silo skirt as opposed to up to the top of the silo. Another thing that we're moving towards is getting our injection rate controlled, tied to unit load and fuel sulfur. Those are our, well, back in the day we called that the Trona calculator, which was based on sorbent testing, which is, it's sort of, you get a snapshot in time, and it's not always the most accurate thing, but it is better than nothing. We've looked at several different SO3 monitors. There's some out there that are fairly indicative, but we didn't really see the value in going down that path for trying to control the units. So a couple other developments that are sort of newer. Going to an air purge at our splitters to clear blockage. I think that's something that was a bigger deal with the old nozzle arrangement, where you'd have like a restriction at the end and a little dispersion plate, where now that's with an open-ended pipe, you can rot it out fairly easily, but air sometimes can't clear those out also. One thing I'm really excited about is using thermocouples to monitor for pluggage. That's sort of been something that we've, as an industry, looked at several different things, but I think the thermocouples are probably the most reliable way to get that information. What you're looking for is a hot nozzle, and what that means is that there isn't air going through it anymore to cool it down. And so once you have stagnant air, you have the heat of the duct affecting that temperature reading. And so you're looking for a hot nozzle. And really, I think more than anything else, that last bullet is probably what I'd say is the holy grail of DSI, and that's dispersion. If you want an effective DSI system that's going to give you good performance, you have to have dispersion. If you don't have dispersion, you're going to have spots that you miss, and you're going to get capped on the kind of performance you can achieve. So with that, I believe we're on the last slide, which is just the dummy blank questions slide. I'm happy to answer any other questions that might have come up.
So I think, Dave, we still got like 10 minutes, but I think we have a question from the audience, and I'm sure some other, me, I've always got questions. So I think this is a good one. This is a question I had myself, was from the audience. Someone asked, Are there any SCR performance impacts that you guys saw when you moved your DSI injection upstream of the SCR?
We have not seen any SCR impacts. Now, ironically, I've done a fair amount of FTIR flue gas monitoring, and one thing that we've found with, at least with sodium, is that you end up getting a small amount of NOx removal with higher sodium injection rates. I mean, it's not much, and the only way to really measure it is if you're not injecting right at the SCR, and this is, I'm thinking of Northeastern, where we would get something where in the range of like 10 to 12% NOx removal. And I believe it was something along the lines of it would push all of it to NO2, if I'm not mistaken. It's been a while since I've looked at that data. But I think with when you're actually injecting ammonia with an SCR, you wouldn't see that. You know, Northeastern doesn't have an SCR installed, so you're getting basically all of your NOx come through and getting hit by the sodium sorbent. But we have not seen any sort of adverse impact on having to inject more ammonia for NOx control.
Okay. If you guys had to operate, has there been anything different in terms of how you guys operate the SCR, or just from an operational, whether it's soot blowers or anything like that? Is that still, you know, again, you mentioned there's a bunch of fly ash going through it. So
all right. So one thing that we have done that I'd say made a big difference for us, you know, we did a long-term injection study, and we saw pretty significant pluggage. So I guess that is something that we put in an ash sweeper system. You know, there's a couple different outfits that do these, and what it is it puts in a jet of air across the top of the catalyst and breaks up any material that sort of can build up there. And it's done a terrific job of keeping our catalyst clean. You know, when we first went in and looked at, so I'm backtracking a little bit, it did affect our performance, but not in a direct way. So what we saw was some pluggage buildup with a test that was admittedly not ideal. But nevertheless, we put in ash sweepers, and they've done a terrific job of keeping the top of our catalyst layer clean.
Are they able to kind of do that online without, or is that something that you guys have to come offline at all to do, or?
Oh, well, I mean, to install the ash sweepers is an outage job.
Yeah.
Running the ash sweepers is something that it runs in parallel with sonic horns. It runs off of air. It's like a series of air cannons that go off in a sequence.
So, Dave, you're getting a bunch of questions come in, so I'm going to try and ask them as best as I can. As it makes sense with the conversation, we may circle back a little bit, but so with those air sweepers, it sounds like there were air cannons or soot blowers. You already had something for catalyst management installed. So was that sustained? Did you also have that used in conjunction with air sweepers, or what was kind of the before and after in terms of keeping the catalyst cleaned off?
Okay, so our design basis in general is sonic horns for maintaining cleanliness of the catalyst, and our air system was pretty significantly oversized at Rockport, so we had a fair amount of capacity left over. And when we did the long-term injection test, and we saw pretty significant moonscape of material built up on top of the catalyst, we decided to check and adjust, and we looked at a couple different options, and we there's Formatec, and I believe the other company is IGS. They offer a similar product line. The ash sweepers, we did. Well, I think we went with Cormatec, and there's a different safety screen that comes along with it that we put in, and the ash sweepers in conjunction with the sonic horns and the new screens have done a really good job of maintaining cleanliness.
Okay, excellent. Now, have you guys, by injecting upstream of your SCRs to date, has there been any observations about impacts associated with the catalyst life in contrast to when you guys were injecting downstream of the SCR?
Right. So far, Rockport is where we have the most experience with this. Rockport is somewhat of a unique design for us. Most all of our other SCR units have 4 layers installed. Rockport is only ever going to have 2. We didn't put in booster fans. It's a forced draft unit. So we are sort of in a change out frequently pattern by design. So it hasn't affected it, but I don't think that's really indicative of what we'd expect long term because we are also going down the path of switching from Trona to hydrated lime and injecting at the SCR. But we don't have good long-term data there yet to, I think, answer the question of where that person's going.
All right. Sounds like a good future webinar, Dave. To revisit back, again, you got a lot of questions. We're going to try to get to them all. So I am bouncing around a little bit here, but one of the questions was around the lines of the interaction between DSI and ACI. Have you been able to tell, are you getting any impacts associated with the ACI performance based on, moving the DSI injection location further upstream? Have there been different chemistry interactions that you can kind of share and talk about?
We have tried to go back to a regular pack material, a non-brominated pack. There's a pretty good cost savings available there. We've looked at different options. We've looked at bromine addition to the coal, and from an efficiency and the all-in cost, we have not been able to get away. Brominated pack is our standard, and with injecting upstream, you're basically, since we're targeting SO2, there's basically no halogens left in the flue gas because they get reacted with first before SO2 goes. And since we're targeting a pretty substantial removal rate of SO2, in the neighborhood of like 75%, there's really no halogens left in the flue gas for oxidizing the mercury. So we need brominated pack to make that work.
Gotcha. Okay. Did you see anything about your usage rates? Have those changed at all in terms of the brominated pack from those injection locations?
I really don't have a good feel for that, quite honestly.
Okay.
I know, and I'm talking specifically Rockport. Every other unit where we use brominated pack, the biggest issue is injection rate turn down. So we're using very little of it.
Gotcha.
At Rockport, we're in the hundreds. I think it's roughly a pound per megawatt is sort of where they're at for injection rate.
Okay.
I could be out of date with that one, but I think that's in the ballpark of what they inject.
Okay. We had a question. I know you mentioned NO2 earlier. I think that's when this question rolled in. Have you guys had any issues with like a brown plume as a result of like an increase in the NO2 formation when using the sodium sorbents?
No, we have not seen any, not heard any, I've not heard about any sort of brown plume associated with NOx and sodium sorbents.
Okay. Let's see, we have a question about the CFD modeling, and have you guys used the CFD modeling ultimately to optimize the injection lance configuration? I assume that's in conjunction with the Delta Wings. And if so, kind of what do you have like a goal or a metric that you guys are using for dispersion to kind of recognize that you've got the process design dialed in based off of what the modeling is telling you?
I mean, I will admit that we don't model every unit now. When we did the Rockport CFD model, we got to a pretty solid RMS. I can't remember off the top of my head. It was, I want to say it was like 40% was where it went from like having a few gaps here and there to basically having it all pretty evenly dispersed.
Okay. And we did have a question too about impacts on the Delta Wing when you're injecting sorbent into it. And I know that you'd mentioned, with the camera, you saw like a little bit of buildup, but we weren't necessarily, it was kind of a trial, not necessarily an optimal location. But do you guys have any long-term experience in terms of like just like any buildup or anything you've observed on the Delta Wings?
So one thing that we have seen is you end up, and it's not necessarily at the Delta Wing itself. So it's usually at the first place where the material impacts a sort of a stiffener or any sort of obstruction with sodium. That's where you tend to get material buildup and slough off. So we saw a fair amount of material that would build up on our turning vanes, and it would grow and then slough off, and that was the kind of stuff that was happening with the that first wave of pluggage. And so I think what the ash sweepers are doing is sort of breaking those chunks up into stuff that's small enough to pass through. At least that's what I'd like to think is happening.
Okay. Do you have any feel of how well the CFD modeling results affect, like how they compare to the actual results when you guys got into the field?
We haven't done any sort of like a velocity traverse to try and match that. I guess this is where you sort of get a little pragmatic. And if you didn't see the kind of removal rate performance, that's where we might sort of look a little deeper into things. But we were pretty pleased with what we got, so we didn't go down that rabbit hole.
Okay. All right, we got two more questions. I know we're a couple minutes over, but these have been great questions, so want to keep them going. So we won't take any more questions. If anyone has questions after these next two, then send us an email and we'll get with Dave and get a response for you guys. But yeah, great round of questions. So this question is around SO3 control, and the question is, have you observed any different impacts of SO3 control and just the relative efficiency of it as you guys have moved to DSI upstream of the SCR? So the question is specifically around SO3 capture.
One thing that we've seen that I think is noteworthy is that you really need to take a good eye, keep a close look on the catalyst management program. We had an incident at one of our facilities where we had done some performance testing. We got a good curve and it was doing really well. And then all of a sudden, we did some follow-up testing and it looked terrible. And it was a temporary system. It wasn't a great setup. But another thing that we figured out is that there was the last layer of catalyst was in a pretty bad state of disrepair, and it was sort of reaching its asymptotic decay. And it had actually, that layer had been in there for, I think, over 10 years. And it was in pretty bad shape and badly needed to be replaced. So I guess my feedback there is make sure you don't leave catalyst in for too long.
Good advice.
Because
Good
that
advice.
will impact the regeneration of SO3, because especially in our situation where it was the last layer, most all your sorbent has more than likely been reacted by the time it gets there.
Okay. All right, Dave, last question for you. So with milled sodium bicarbonate, are you seeing a reduction in performance when the conveying air humidity is higher? So in other words, they're saying from any kind of particle agglomeration that's causing, say, reduced dispersion?
So we actually did a retrofit here in the last year to dehumidify injection air. That was more around trying to prevent, so obviously with the DSI system, the injection air gets up into the loss and weight metering system with leakage air through the rotary valves. And this was, we did that to prevent humid air from gumming up the process. We have not seen any adverse impacts on SO2 removal performance on a seasonal basis.
Okay. All right, Dave. Well, I want to say you are currently the champion and current DSUA record holder for questions for webinars. So you will go down in the record book and be acknowledged accordingly. But there were a lot of really good questions and great content. And we did run a few minutes long, and we're going to give Stewart a few extra minutes for his too as well. So just want to say thank you, Dave, again, for your time putting this together and participating. And if anyone else thinks of questions after the fact, just reach out to us and we'll be happy to answer them. So thanks, Dave.
All right, you got it. Thank you, Jerry.
Yes, sir. Now I'm going to turn back over to our host, Travis Reynolds, to transition us to the next one.
All right, thanks, Jerry. Okay, so we're going to acknowledge the remaining DSUA sponsors. So first of all, here we've got Noltec, and they are a global bulk material handling equipment and systems supplier or provider. Since 2005, they have partnered with clients across many industries to provide innovative dry sorbent injection solutions. And they have the technical expertise and proven technology to deliver efficient, sustainable, and compliant systems for their clients. Next, we have National Filter Media, and they take pride in being one of the world's oldest and largest providers of air pollution control and liquid filtration products. They have achieved success by adhering to the same business principles practiced since the firm was founded in 1906. They believe in building partnerships with customers and in earning their business every single day. While the filtration technology has changed since 1906, their commitment remains the same, and they want to be a long-term partner with you. So Lechler, for over 140 years, Lechler has been designing and manufacturing spray solutions for air quality control. With a wide range of nozzles, nozzle lances, valve stands, and mist eliminators, Lechler provides solutions for gas cooling and purification, as well as denitrification and desulfurization of flue gases. They advise customers individually and develop solutions to reliably meet even the most stringent emissions requirements. They understand customers' individual issues, and they develop solutions to reliably meet even the most stringent emissions requirements. I think I already just said that one, didn't I? Check out the March 2021 DSUA webinar on YouTube for their presentation at the Jacksonville Electric Authority about SDA optimization efforts. And hang on here in just a little bit where we will pick up a little bit more as well. Gecko Robotics. They use revolutionary robotic technology for industrial infrastructure inspections. They have wall climbing robots and inspection teams that perform NDT inspections for clients across the globe. Their robots enable industrial companies to carry out regular inspections and capture data at high speeds and scale that existing manual methods would be incapable of, while also minimizing the need for human exposure in hazardous environments. Over the past couple of years, Dave Kahn with Gecko has been very instrumental in supporting us with various efforts within DSUA, and we greatly appreciate that. You can also look back to the February 2021 webinar where Michael Paul Jenkins, MPJ as they call him, gave a presentation on their robotic technology being used for dry scrubber inspections. ReadyCam, they provide a range of equipment for flue gas treatment and air pollution control systems throughout various industries. They serve end users with technologies to meet even the most stringent emissions needs in a cost-effective manner. They have a wealth of experience gained from more than 4 decades of operational experience. They are a reliable partner, whether it be a greenfield site or a retrofit, and they are capable of helping you achieve your desired air pollution control objectives. Salvatore Gallo is also a DSUA advisor, and he has volunteered a significant amount of time to supporting us in our various initiatives as well as these webinars. Mississippi Lime is a world-class producer of calcium products, including quicklime, hydrated lime, and calcium carbonate. They have over 100 years of experience producing products from one of the richest limestone reserves in the world, supplying products throughout North America and the world, and over a dozen plants and terminals. MLC products produces a high-quality quicklime and hydrated lime, as well as cost-effective products utilized by SDA, CDS, and DSI applications. Kurt Bean from Mississippi Lime is an active DSUA board member who has been serving in this capacity for a while now, and we greatly appreciate his time and contributions. You can check out the March 2021 DSUA webinar on YouTube for their presentation about enhanced hydrated lime fundamentals. So once again, we want to thank all of our sponsors. The screen is getting quite full with our various sponsors that we have. So a huge shout out to them, because without them, this would not be possible. Jerry, I'm going to hand it back over to you.
There we go. Now I'm off mute. Yeah, just wanted to, so our second speaker, Stewart McKenzie of Lechler. Wanted to give a little background on Stewart, and I'm going to kind of, this next presentation will be a little different. I'll give you a little bit of background on it, but Stewart, his educational background includes both a business as well as a technical, as he's got his MBA as well as a bachelor's in Chem-E. So he's well-rounded in terms of both commercial and technical solutions from Lechler's perspective. He's got a pretty broad experience in different applications. So, you know, cement, chemicals, power, mining, paints, coatings, alternative fuels, and over his 30 plus years of experience in his career. So his experience includes from working at large corporations like FMC, DSM, Mitsubishi, as well as even startup companies like Vapor Technologies, Allied Photochemical, and TrueLight. So he's been at Lechler since 2014 with a focus in the cement and the power industries. And currently his role, he focuses in the geographic region of the southern and mountain states, but he's also, you'll find him hanging around Texas and California as well. A big shout out to Stewart. He's also, again, supported us with DSUA from an advisor role and supporting sponsorship and just an active participant. So again, he's volunteered his time to help contribute to DSUA. So we thank him for that. So Stewart, we will give him some extra time. Anyone that has to hop off at 11:30, again, this will be recorded. The genesis of what we want to talk about with Stewart, this is intended to be sort of a pseudo panel in the sense that we've kind of got some questions rather than Stewart having, you know, slides to present and run through the traditional format. And a lot of this came from Stewart and I had a really good extensive conversation about CDS nozzles, and it was really interesting because while we've titled this kind of dry scrubbing, you know, 101, nozzle 101, I think a lot of that information, especially around CDS, ends up being honestly information I think, you know, end users don't necessarily know. You know, I think it becomes really critical because some of the issues we've heard talked about in webinars has a lot to do with material buildup and the ducts and the bag house and bridging and hoppers, and I think a lot of it can be attributed to things around the nozzles. And I think it's so I thought it was very educational. So the thought was, you guys have questions, we're going to kind of throw out general topics. We've got some questions that we want to give Stewart a chance to talk to, but if anyone in the audience has questions, just fire them away and we'll filter them in as needed. So you'll find this is probably going to be a little more CDS centric in terms of those nozzles, but there will be also discussion around SDA nozzles as well. So don't feel exclusive that if you've got a question about something with SDA, fire away and we'll ask Stewart. So, so the first general topic that we're going to talk about is going to be around nozzle design in general. So, Stewart, some of these again may seem elementary questions, but I still feel like there's a lot of people that could learn from them. What essentially, I think a lot of people think they understand this, but from the terms of a primary objective of the spray nozzles and a dry scrubber, like what is it about the design of those nozzles people should know that it achieves the goals of what that nozzle is intended to do?
Well, in DSI specifically, we're really talking about humidifying the sorbent that we're accompanying. And as Dave indicated, he wanted to keep that around below 5%. That's very difficult to do without a precision nozzle system. If your nozzles are pretty complicated and pretty sophisticated in their design. Can I share a couple images with you, Jerry?
Yes, sir.
Okay. The first and foremost thing is that there are basically two types of nozzles. And did you get that? You see all that? You must see.
No, we don't see your screen.
Okay. Now do you see my screen? No.
No, sir.
Okay. Technical difficulty. I apologize.
That's all right.
So there are basically two types of nozzles. One is what we call pneumatic, which is air atomized spray. You're taking the energy used in or that's found in compressed air, and you're using it to atomize the liquid that you're spraying in. I don't know why I can't share that. Well, anyway. So the first one, air atomizing, gives you a significantly better turn down, meaning you can go from a high flow rate to a lower flow rate. The turn down is usually like around 40-1. So if you're at, let's say 40 gallons per minute, you can go down to 1 gallon per minute with that spray. Or if you're at 10, you can go down a factor of 40. The second is hydraulic atomizing. That's where you use no compressed air at all. This has been very popular for saving in energy consumption, so you're not compressing air and things like that. There's two types of this as well. There's a simple hydraulic where it uses an interference method where the liquid basically hits a pintle of some type, spreads out and gives you the atomization that way with force. And then there are other ones like our spillback systems that really just use the flow of the water, the channeling of the water, rather than impacting anything. The advantages to spillbacks is that you don't have the wear that you would have seeing a liquid or a slurry like that impact a particular obstruction within the nozzle.
Mm-hmm.
So with that said, again, the nozzles and spray systems are more sophisticated than your backyard hose. You can put your finger over it in the hose and get a nice spray, but for industrial applications, you're looking at precise control of in a very harsh environment. So that's what Lechler has used its 140 years of existence to perfect, in a number of applications. We not only participate in process industries, chemical industries, cement industries, lime industry, things like that, but we also go into waste to energy and a myriad of other industries. The three that I focus on, of course, are cement, power, and waste to energy.
So in terms of the nozzle design, one of the things that you and I talked about offline that I think is interesting is the use of the barrier air.
Yes.
Maybe you can kind of share with folks a little bit about that, because some folks, as I understand, don't have barrier air to their CDS nozzles. Some do, and frankly, some may not really understand the important design parameters and what it's for and what they should be looking for to make sure it's doing what it's intended to do.
Yes, barrier air is a low pressure, high volume curtain of air that comes out around the nozzle. If you can see this is a nozzle. I think this weighs probably a pound or so. And what we do is that we put a sheath around this nozzle all the way back to the lance and blow that blower type air, again, low pressure, high volume, around the lance and the nozzle. And what this does is a couple of things. One, it helps cool the nozzle and the lance to prevent metal fatigue and things like that. But also with a curtain of air coming out around the end of the nozzle, what you're not seeing is a lot of aerosolation that causes the buildup and everything on the nozzle itself. So it keeps the nozzle tip nice and clean without bearding and things like that. There are limits to that, primarily that once it's set based on what the spray is actually going to do, what pressures, what temperatures and things like that. So going in and raising the flow rate or raising the pressure that you're using in barrier air is not always a good thing. More is not always better. We've optimized it based on the design of the nozzle and the flow rate respectively. Okay,
that makes sense. So to me, the important takeaway for folks to know is one that I guess recognize if you have that air or don't have that air. And I think from what we've talked about, that sounds like if someone doesn't have that, that could be something that's retrofitted later, but the operational parameters are there for a reason. And if X is good, 2X doesn't necessarily mean it's better, and it may actually be a detriment is kind of what I think people should take away from that.
Now, okay. And one thing to understand is Lechler's been involved in designing these systems for quite a long time, and we've really optimized this. It's more sophisticated than just putting a large pipe around a small pipe. It's really the computational fluid dynamics that we depend on to tell us what is right and what's wrong and what's optimized for that particular system. But with that said, each system is different.
Well, and the last thing before I know we'll turn over to Travis, going to handle the next topic, is so the folks that don't have barrier air or aren't using it properly, I guess if all those issues happen, you talked about bearding, et cetera, you know, what are the associated impacts that the barrier air, what are the benefits of the barrier, I guess, in terms of the process is concerned with?
Well, again, it's primarily, can you see my slide yet?
No.
Okay. It's primarily cooling the lance and keeping the end of the lance cool and clean. It keeps the smaller particles, which aren't necessarily going with the majority of the flow, and that have a tendency just to hang out in space and deposit on nozzles. It helps keep that clean. So it really reduces the maintenance costs associated with running lances and nozzles in your system.
And as far as the lances, you know, those maintenance costs, I mean, and I think of the operational parameters like we talk about like the importance of spray angle and particle size distribution. I assume that as you get built up and if you don't do that maintenance program or have that barrier air, then you start seeing impacts associated with the spray angle and the PSD, the atomization ultimately, and that can lead to.
Absolutely. As you build up anything inside or on the outside of the nozzle or in the lance, you will see differences in pressure, fluid pressure. You'll see increases in your air pressure and things if you're using what we call twin fluid or air atomized system. So If you have the luxury of being able to put pressure gauges on each one of your lances, you can really monitor those closely. Most people put the pressure gauge just on their header and they watch for that to rise. The only issue there is that there's a lot more volume and it's a lot more inertia in that system to read any change in pressure.
Gotcha.
Okay.
Okay.
All right. Hey, Stewart. So you talked a little bit, so the nozzle, obviously that's kind of the business end of what's doing the dirty work here. But, upstream of that, you have your lance. Can you tell us a little bit more about, what determines a proper lance design? What do you look at when you develop that? I guess you probably need to look at that depending on whether you're looking at hydraulic, pneumatic, all that. You care to give some thoughts?
Certainly. The lances that we design are optimized to work with our nozzles. You really can't take our nozzle and stick it on the end of a pipe. That's going to be an issue. The nozzle won't work the way it should. It will get usually insufficient amount of fluid going through there or air going through there. And you can really cause large issues by using the wrong lance because it's either going to get too much or not enough of the feed that it requires. Size is a big issue. What we really do as far as length and positioning of it is look at your vessel, see what specifics and anomalies you have within the vessel, and we will locate where those nozzles need to go, and then we build the lance on to put the nozzle in the right place within the gas stream. So it's very important that you don't have them too far in or too far out. There are adjustable lances that you can move in and out if you want. The only problem with them, it does give the operator a little bit too much control. They have a tendency to play with things that they can control and may not put it back to exactly where it should be. But if you do have a good maintenance program, Lechler's happy to come out, provide you some training and overview on how to use the equipment, have our field engineers come out and go through the whole system with you if you want, be it a commissioning system, or if you have you're having trouble, give us a call. We'll be happy to stop out and take a look at that as well.
Okay. So you kind of went ahead and alluded to the next point there, and that has to do with maintenance. And obviously, as you said, your maintenance is going to be very specific and unique to each plant, their specific application, what their conditions are. If someone were to ask you just as a ballpark, what are your recommendations for nozzle cleaning frequency? What do you say to that kind of question?
Because each plant is different, each vessel, each system is different, and we design them custom based on what the operation parameters and goals of that company are. As far as frequency of nozzle change, we tell them to determine that empirically. When you first install a nozzle, it's clean, it's going to be working perfectly. I would go, and I typically say, pull it out after a day, see if you're getting buildup. If not, put it back in, let it run a couple more days, pull it out, take a look at it. And in whatever time frame that you're doing that, you can see the frequency of which the buildup is occurring. So I would base the PM on that. And at some point, we have customers who aren't doing any significant maintenance other than maybe once a quarter. So it really depends on the operating environment as to when the maintenance is done. But it's how the maintenance is done, which is even more important. Again, these are precision instruments used in an industrial process. So care has to be taken with these, with the lances and the nozzles. Remember, you're normally pulling them out of a hot environment. So you have to wear gloves and be very careful that you're not going to get sprayed back. You want to make sure that all your connections are disengaged and so you're not getting hit with hot liquid or anything like that. And then when you actually go into the cleaning of a nozzle, some people have used welding rods to try to clear obstructions, a variety of different things. We suggest plastic or brush type materials to do that, because if you if you use a metal or a very abrasive surface, you're going to hollow out or rim out the nozzle orifice. And if you do that, it's going to completely change the flow and spray characteristics that you're experiencing. A lot of people will, look at a nozzle and say, yeah, that's a little built up. So I'm going to stick this little welding rod in here and wring that thing out and get it nice and clean, and we'll have wonderful air. Well, no, that's not going to happen, because you're going to get more air in here, and that's going to throw off your balance, because one, this side will be bigger than this side probably, and that's going to impact your whole spray characteristics. So as a rule of thumb, treat these things like they cost several $1,000s, which they do. Don't throw them on the deck when you pull them out of a reactor. Try to not bang the tip on anything hard. And if, again, just a simple PM program is really all you need.
Okay.
More importantly, treat them as if you don't want to be in a baghouse hopper, cleaning out buildup and scraping buildup off the walls of a reactor, CDS reactor wall.
Absolutely.
No, honestly, I think that's great input. Hopefully it's like things that people take to heart, because, for me, hearing those solutions, the biggest concerns people have for, say, a CDS system, and I hear in SDAs too, so I think the theme is true, is the build up, excuse me, things like build up and those concerns. So on that note, in the field, what are some of the, so if you're an operator sitting in a control room, I like your advice about, get a feeling of pulling your nozzles out, looking at them, and, if you're a new user, to understand what it looks like. But if you're just looking at, operational parameters, you got any tips for users out there of things they should be looking for, trends they should be looking at, so you can kind of catch their eye to say, all right, maybe I need to go pull my nozzles out and look at them?
Well, if you're in the control room, what you're looking at are temperatures, pressures, and volumes. So if you're monitoring a spray system, any change or increase or decrease in volume or pressure is indicative of something that's happening. So if that happens, I would have someone take a look at it. But by taking a look at it, what we recommend is putting a test stand, which is basically something to hold the lance on the same deck as where the lances are mounted, and hook it up to a water source as close to the operating parameters as you can, given an independent water source versus a slurry or something else, and spray that out into the air. You can look at the cone and draw a lot of conclusions on what is happening and or what has happened to the lance. For instance, if you're spraying this cone, the cone should look nice and uniform and come out into a cone. Sometimes people will change their parameters, either flow or water, and they'll get a nice straight jet out of what is supposed to be a hollow cone nozzle. So, so you spray that out, you look at the first couple feet of it and make sure there's no fingering. That means any dense spots of liquid that are flowing out, rather than a nice smooth cone, you're seeing fingers that are coming out like this. And any of those odd behaviors is indicative of some kind of maintenance issue. It could be a broken or a damaged nozzle, could be build-up. It could be a lot of things, but again, Lechler's there for you to teach the users on what to expect.
So you're saying all your customers go out there and take videos of them using their spray stand and text it to you and let them know?
Not all of my customers, but I have customers who will do that. What do you think of this one?
It does. I know it's not necessarily precise, but in a crude sense, like it in a way, it makes sense, because they may not know exactly what they're looking for, or may not have the perspective to see something that you guys would. So,
right. And in this world of COVID that we're living, a video is appreciated.
Yeah, absolutely.
Hey, Stewart, we got a question in from the audience here. Have you ever, or has anyone at Lechler ever compared slaked lime versus a purchased, I guess, hydrated or a solution, lime slurry solution for nozzle efficiency?
Yes, we have. there have been several customers who prefer to make their own lime solution because if they think it saves money and things like that. The only issue that I've seen is the actual agitation of the finished material. You got to make sure that all the lime that you're putting into the slurry actually gets dissolved to the point that you want. There's been some customers who use a pebble lime for this. They'll put a pebble lime in, then they'll put water in and agitate it for a little while. And if they don't allow enough time for that to get in solution, you're going to see a very large particle clog up one of your nozzles. That kind of thing is why we recommend customers go with the hydrated lime and or purchase the solution as is from Loast or Carmeuse or Graymont, all those others. Did that
Okay,
answer
cool.
your question?
Yeah.
Okay.
I think so. We'll see if another follow-up question pops up. One more question on just maintenance activities, just for folks to know. What in general for life expectancy of the nozzles, and I know this is probably dependent a little bit on people's PM plans and whatnot. What have you seen for just in terms of nozzle life? What should folks expect from? And I guess what's the spectrum you've seen based on how well people are taking care of their nozzles or even their operating environment?
We've seen that our nozzles, because they are designed with the specific environment in our thoughts, we will choose materials very carefully. In some applications, particularly when we're dealing with the slurry, you want to use a ceramic type of nozzle or nozzle insert. To do this, reduces the wet wear that you'll see in that nozzle and reducing the amount of maintenance. We have some customers who will take out their nozzles routinely, take a nozzle out a week, put it in a offline, quick connect wash box, and they're coursing vinegar through their vinegar solution with a little pressure, and they'll let it run for the day. And in the meantime, they've replaced that nozzle that they took out, and they have seen 3 years of usage without any significant buildup. Others will take it out of the package and throw it in their toolbox and come back and install it later, and there could have been some damage there. Again, we have a complete list of maintenance practices that we can offer you. You can just send me an email and I'm happy to send it to you, but it tells you what to look for, how to clean it, and things you can do to improve the overall life of the nozzle. But our nozzles, again, are highly sophisticated, but they're industrial grade. They will last years if you take care of them.
Okay. We got a question in from the audience just then. So as a follow-up to what you just talked about, are you saying that you're recommending lime slurry injection in a CDS as opposed to just water injection with dry hydrate addition, or what? Can you clarify that?
Into a CDS, I'm only recommending water injection. Again, it's about humidification. In a SDA type of environment or in a wet FGD type of environment, that's when you're really looking at slurry, and that's when materials of construction are really important, because not only is that the lime abrasive, but it can also it's also reactive if you use the wrong material.
Okay. All right. Thank you. So one more question here before you carry on spare parts inventory type stuff. What are your recommendations on quantity of spare parts, inventory to have in stock on hand, and what's a typical lead time for?
Let me
parts?
address the last question first. Lead times aren't short. They can range these days, given all the supply upsets, rising material costs, world conflicts, etc. It can take 16 to 20 weeks, 3 or 4 months to get a very sophisticated nozzle. Why is that? Because almost all of our nozzles, the sophisticated nozzles, are manufactured in our plant in Germany, and they do a great job. And you can rest assured that their German engineering prowess is in full use. What I typically tell them, again, based on your maintenance frequency, I would have 1 or 2 nozzles replacements available. And then I would keep that, the order point probably at 2. And then see how your system goes. If there have been some who, like JEA that we did the webinar with, they haven't bought we installed the system in 2018. They haven't bought another nozzle from me yet because they're all working fine. They have a wonderful maintenance program going, and they have instructed the operators on how to care for them. So it depends on the situation that you're dealing with in your plant.
So I know we're at 11:31. For those listening, we're gonna go for another 9 minutes, just to make sure we get enough the content Stewart gets a time to talk. We have some more talking points. If you have to hop off again, come back and check out the recording if you want to catch the last 10 minutes. But so Stewart, that's a 9-minute heads up, but we'll keep going. One of the things you and I talked about in the past too that I thought is really interesting was about the water quality and the system design leading up to generating the water quality that makes it to the nozzle. Really, what you're sitting from the perspective. I'm the perspective of an end user that doesn't know anything about it. What would you want people to be aware of in terms of just what are they looking for water quality? And what can they control in terms of the design of the system that's feeding the water to the nozzle?
Okay, when you're spraying water into a vessel, the biggest thing is the water quality itself. You don't want to have any suspended solids, undissolved solids in the solution in the water. This can take the form of alkali materials, things that will cause high hardness. Typically for a twin fluid type of nozzle where you have the air doing the atomization, we can go up to about 1,000 ppm of total solids in that solution without any kind of issue at the nozzle, without any kind of buildup. But if you're using a spillback system, which operates at much higher pressures, about 500 psi, you have to basically cut that down to a third, or about 300 ppm of TSS to really keep that nozzle in good shape. Because the pressure is higher, and because the dimensions of that nozzle are a lot more sophisticated, where we're having backflow as well as forward flow for the injection, it's very important that that you monitor your water source. So if you have a bad water source, let's say you're pulling from the quarry, which a lot of my customers do for cooling water, we recommend a variety of things. Simple screens, a filter, a pre-filter into a holding tank would be wonderful. There are inline screens that we can put in either prior to the pump or just prior to the lance, depending on how the operation is running. In most cases, it's pump restrictions that limit you on your water quality, because the pumps are rated for a particular amount of suspended solids. And if you want to reduce the amount of costs associated with that pump, clean your water up.
Makes sense.
Yep. So we got another question from the audience here, and it's a really good question. I can't believe we didn't think to ask it. When you are designing nozzles for a CDS scrubber, what information do you require to get started in developing that design, and do you recommend any CFD modeling as part of that?
Lechler has a a series of process data collection questionnaires that we are happy to provide you. It tells us about flows, pressures, vessel designs, and your targets. You know, if you're you want to get 5% or less than 5% relative humidity injected, we'll take all that into consideration. So at bare minimum, it would be what are you trying to achieve? What kind of issues are you looking at? And all these things come out of the questionnaire. We would need drawings of the vessel that you're looking at, in which you want to install something, so we can do a real close analysis of it. And yes, we do use CFD in cases where a plant's been around a while and there have been some unofficial engineering done on the system itself. So we like to see the CFD that's offered usually as an option in one of our quotations, but in some cases we'll say we have to do that if you want a guarantee of dryness or reactivity or some other guarantee from us. You really do have to take a look at that, because there have been situations where companies are having problems with water cooling, and they tried a bunch of different nozzle and lance suppliers, and come to find out that their cooling tower or whatever vessel they have in it has a big swirl, a big vortex being created inside of there because of the way the air comes in and creates everything. Well, that isn't particularly good for gas cooling or for reactive sprays. You want typically a gas rate that's 15 meters per second or less, so you can get good interaction either for heat transfer or for reaction kinetics. And other than that, that's really what we're looking at.
So
Okay.
we did have a question from the audience. The comment, and then the question was that activated carbon, just carbon in general, is very abrasive. Have you had any experience with, say, activated carbon contributing to any nozzle abrasion, anything like that, or even brominated pack for that matter contributed to like corrosion? Any comments or experiences related to that?
We try to position the nozzles where they will see the minimum amount of abrasion from solids and things that are being injected. There are times we'll have to put a guard on the nozzle to protect it from the solids that are coming in. They work quite well, still allow you to put in the amount of moisture that you want, but it protects it and does contribute to a significantly longer wear. So yeah, there's a variety of things. Again, it really comes down to what is each customer dealing with. And we have a great engineering staff in our St. Charles, Illinois facility, and they've seen everything. And,
so is that more related to just dust loading in general? I know the question was around carbon. Is that more just about solids material and less of a concern about what the chemistry of the solids is necessarily? That makes sense?
Yes, it's more about the solids, the nature of the solids, because we're talking abrasion of the outside of the nozzle. We haven't seen anything that would come into the nozzle and change the flow characteristics, but yeah, it will tendency to wear the nozzle and the lance if it's unprotected or if it's in the stream of flow of the DSI.
Have you seen that be a concern with CDS systems? Like, I know if the nozzles are placed above, say, a venturi, you may have a lot of dust loading coming through there. Is that typical to find that CDS systems would have a guard or some form of protection to ensure that you're not getting some abrasion there? Is that common with CDS?
As a rule of thumb, no, that's not an issue. But in a CDS, because it is all dry and everything, I would recommend some barrier air where you're pulling, you're keeping the things away from, keeping the buildup away from the nozzle tip. And that usually results in any kind of wear issues or impingement upon the spray equipment.
Gotcha. Okay.
So Stuart, we'll probably do one more question here since we are up against the time limit, but just
Certainly.
kind of lessons learned. You know, you talked about barrier error just then. You've talked about a lot of other things. What are a couple of key lessons learned that you've seen from working with customers, things that they may have done improperly? Just a couple of key things that you can throw out there.
Well, my number one thing is understand that Lechler sells not only to the end user, but we also sell to the EPC houses, the OEMs, and invariably the systems get installed by local installation labor. Now, my customers are they're all smart, they're all geniuses. And but when it comes down to local labor, they don't always have the same mindset. So you really have to be careful that if a particular pipe size is specified, that pipe size is indeed used in the system. I'm going to give you an example. I'm not going to name names, but we recently had an EPC who bought a system from us for installing at a plant. They had barrier air on their injectors, and as soon as they fired up the nozzles and everything, they were complaining about buildup on the nozzles. And why are you getting buildup when you start up? Well, they said, we don't know. We want you down here now. So next day I was there and we went through the whole system. Come to find out, it was a barrier airline that had some problems. Because it's low pressure, you have to give it a nice large cross-sectional area for that air to flow through and to reach the lamps. In this case, we had specified a 6-inch diameter feed pipe, and what was installed was a 2-inch diameter feed pipe. So not only was it restricting flow, it was increasing the pressure significantly. As I said, we had designed it to work in a specific range of conditions, and that is all dependent on installing the equipment as it is specified. Now, we said to put in a 6-inch diameter pipe. They put in a 2-inch diameter pipe. I'm not sure where the issue arose, but that's what they put in. And so to the end users, I would say be careful. Make sure that your installers are experienced and they know something about spray systems and injection systems. If they have any questions, call us. Let us know. We're happy to talk to them on a phone, Zoom call, come and visit, and go through the whole process with them.
Yeah, it sounds like with a lot of things, the devil's in the details, and say the uneducated mind in terms of understanding the process, that it's really easy that what appears to be a minute detail can have a non-trivial impact on the performance and the efficiency of your process and the associated O&M with it. So I think that's a good way to kind of end this, Stuart, because to me, that was the essence of a lot of our discussion. Hopefully that's what people are getting out of this, because I feel like in a lot of ways from end users I've worked with and talked to, existing and new, that this is kind of an overlooked thing, and all the things they're concerned about and scared about with these solutions, a lot of it can be dialed back to something associated with how moisture is introduced. And so to me, it can be a fixable problem. So thank you for that. Hopefully folks got some good stuff, and I'll turn it over to Travis to kind of take care of us and this out. Thank you, Stuart.
Yep, thank you. All right, well, I want to say a huge thank you to the presenters today. I mean, we can't do it without you, the sponsors. Once again, thank you. To the participants and viewers today, this will be loaded up on YouTube just as soon as we can get this downloaded and saved over there. If you're looking for any more information, you can go to the DSUA website, look us up on LinkedIn, or you can shoot us an email. Do what we can to help you. Be on the lookout for an email for next month's webinar. The topics are yet to be determined, but if you have any ideas for abstracts, feel free to shoot them over to us, and we'll talk to you about getting you in on one of these webinars. So that's it for today. I hope you learned something. Hope you enjoyed it. Feel free to fill out that survey when you see it, and have a wonderful and safe day.
Thank you.